Welcome to Partial Differential Equations Lecture 3. We're going to continue looking at the Cauchy problem for solving quasi-linear first-order equations. As I said in the last lecture, we started developing this geometric picture of what the equations actually mean, and we're just going to push it a little bit further today. So just a reminder, what we're actually solving is the quasi-linear equation. In other words, it's an equation of this form. It's linear in the highest derivative, and we're only considering first-order derivatives. And it's quasi-linear in the sense that the coefficients of the linear derivatives can contain x, y, the independent variables, as well as u, the dependent variable. Okay, so that's the general structure we're looking at now. And if you recall from the last lecture, I said that all first-order equations can have a solution that can be reduced to integrating ordinary differential equations, and this is just the first category that we're looking at, mainly because the simplified version allows us to form our intuition more carefully before we look at the full general problem. So the situation we had is something like this. We had the theorem the last time as well, that we viewed the solution space to this quasi-linear equation as a surface z is equals to a function of u and x and y, where we don't yet know what u, x, and y is. We do, however, know that the theorem we proved the last time, that this surface is the union of all characteristic curves, and vice versa. Should you find the union of all characteristic curves, you would form the surface that actually describes the solution surface to that problem. And just to remind you what a characteristic curve looks like, it is a curve that has the tangent vector pointing in the direction of A, B, and C, where A, B, and C are these functions over here. Okay. And just one more thing, we also had the idea of the normal to the surface, and for a surface that's described in this fashion, z equals to u of x and y, the normal is merely the gradient, and there we have its derivative of the function that describes the surface. So that's basically u of x, u of y, and minus 1, because you put this whole function equals to 0. Okay. And then what we're going to do is we said that that was the abstract solution, this idea that the surface is the union of characteristic curve, or the integral surface, which is the solution, is the union of characteristic curves, was an abstract solution. We don't know what the solution is, but we were able to explore some of its properties. And then the Cauchy problem is when you actually try and find a specific solution that satisfies certain things or data that you know about the problem. Okay, typically this data is specified as the initial condition. For the Cauchy theory, however, it's completely general. And it's general in the sense that you basically specify any curve, which they call the Cauchy curve on gamma, okay? And you specify it as a parametric curve, so you basically are specifying its coordinates in terms of a function of parameters. So you basically specify this Cauchy curve, and so there you have the x coordinate, which we denote by the function f of s, you have your y coordinate, which is g of s, and then you also specify the function, which is basically z, which is h of s. Okay, so this stuff in purple is given, your equation is given, and we're now going to work out the implications of that. Okay, and also we already know from this equation that the solution can be represented as the surface, and that the characteristic curves, which are basically curves whose tangent are that, lie within the surface. So in this figure, what you can think of is let these black lines, or some of these, or rather let the blue lines indicate the characteristic curves for now. Okay. So what we're going to assume in exploring this further, or in exploring basically the existence of a solution that obeys both the quasi-linear equation as well as the prescribed data on the Cauchy curves, for now we're simply going to assume that all functions are C1. It simply makes the proof easier. As I said the last time, you can find solutions to an equation like this that are C0, and we'll look at them at the end. They often are used to depict shocks. You can also find discontinuous solutions, okay? But then you have to have a look at a whole bunch of special cases when you prove the theorem, and it's just becomes too complicated or integrated I basically want to convey the basic idea now. But I'm just telling you you have to do more work, but there are things you can say about systems that are less continuous in C1. Okay, and for the purposes of the exploration, we're going to focus on a specific point. Okay, so it's a local analysis. And this is typical of many of the analysis initially. You basically start making expansion about a specific point. Okay. There are things that you can say about global properties, but we're not going to do it in this course, and you basically need to look at manifolds and topology to be able to do that. So that's not the subject of this course, but I'm just saying that you know the context right now. Okay. We're going to assume that P0 is this point over here around the point that we're focusing. It has coordinates, and because these coordinates lie on the Cauchy curve, you can also indicate those coordinates as that, where I've simply used the fact that we have this Cauchy curve evaluated at S0. Now the integral surface, which is basically this yellow surface, consists of all the characteristic curves, which we proved in the last lecture, and here you can see them. You have gamma S that starts at this point of the Cauchy curve. You have this other gamma S0 that's actually going through the very special point that we're considering, and you have this whole array. So this yellow integral surface is basically formed by a whole almost quiver of these Cauchy curves. Okay. And what else we know? And all those curves basically go through gamma, because we simply specified the Cauchy curve as a curve on the solution surface. And near the point P0, we can actually build up a parametrized surface of the solution surface. And we can view it as a parametrized surface not in X and Y, but rather in S and T. Okay, so we're basically choosing a set of coordinates that's used to describe the surface that is adjusted to that point. So it's valid locally near that point. Okay, and we express it in this way. We simply say the X coordinate is some big function of S and T, the Y coordinate is some function of S and T, and the Z coordinate is some function of S and T. And because it's a surface, you can always represent it with two parameters. Okay, so we're simply making the expression of the surface more parametric. Okay, at t equals to 0, we're basically choosing this parameterization to reduce to gamma. Okay, so basically at t equals to 0, we're on this purple curve. As we move away from this purple curve, the t increases. And so what we've basically done is we've chosen our coordinates to simply be adapted to the Cauchy curve that we've done to make the analysis easier. Okay, and so we also have for all S and T the description of what X and Y and T are is simply given by this, because we know that the surface is swept out by our characteristic curves. So for each of the parameterized functions, we can simply have that X and T, or X of T, Y of T, and X of ST, Y of ST, and Z of ST are defined by the actual characteristic equation. Okay, so we have X, or the derivative of X with respect to T as we move off our Cauchy surface. It's simply given by this. Y of T is simply given by B, and Z of T is simply given by C. Okay, and if there's still vagueness here, you do need to go back to the previous lecture and actually see where it comes from, because it basically comes from the definition that these blue lines are characteristic lines, and the definition is that the tangent to the blue lines is equals to TC. Okay, so that's where that expression comes from. So I'm just basically rewriting in a consistent formulation what we said the last time. Okay, and we also have that these functions obey the initial conditions that when t equals to 0, they reduce to the characteristic curve. So this is just actually reiterating mathematically what I've been saying all along, and we express it in the following way. It's simply x of s, t equals to 0, so you're on the curve, is simply what we've specified the Cauchy data to be. And so that holds for y of s is just g, and z of s is just h. Okay. So what we're building now is a way of actually solving for the surface when that is suited to that specific characteristic curve. Okay, and so now the conditions for the existence of the solution is what we're going to work out. And the way we go about it is, let's now transform back to the equation, or the Cartesian-like equations, or x and y, the original independent variables that we were considering, and we try and express them in terms of these new variables that we've used that were adjusted to the actual initial data that we specified. Okay, and the way we can do that is we basically, to get the connection, we need two equations. Okay, and the two equations we have are just here already, right? We have x as expressed as a function of s and t, and y expressed as a function of s and t. And to actually get the reverse, we can invert that. Okay, so we basically we want to express x and y in terms of s and t, and we simply use the first two equations and invert them to get that. Okay, so it's possible to do that with a caveat that the actual inversion must be able to take place. Okay, the moment we've expressed s and t as functions of x and y, we can then also express the solution u of x, y in terms of using these functions, right? We basically know from our parameterized surface that's adapted to the Cauchy data that u is equals to z of s and t, and so instead of s and t, we now replace what we know s and t to be in terms of x and y. So we actually have u, x, and y expressed explicitly this way. Okay, and therefore we have a representation of actually our integral surface. So now let's go back and we focus on point P0, and we work out rigorously what the conditions are that you can actually do this. And the conditions that the solution can exist locally is basically saying that if it exists locally, we've solved the Cauchy problem. Okay, and the conditions are, and the conditions are basically that this transformation exists and is smooth. Okay, so our assumption that we have the C1 functions is now starting to become important. Okay, so this is basically the mathematically rewording of the Cauchy problem is simply the conditions that ensure that the solution locally exists, given the data we've given. Okay, so here's the same picture. What we're basically going to do is focus on this point P0, and we immediately know that x0 and y0 is equals to that. And then we have an implicit function theorem that basically says the solutions of this equation, we get s and t explicitly, that should be a t in terms of x and y, where we're given this is only exists if the Jacobian is non-zero. Okay, in other words, if that transformation is invertible. Okay, so so that's just writing out the whole thing. And what we have now is that at S0, so at that point, and in the neighborhood of x0, y0, we want to use this implicit function theorem basically to write down the conditions that the solution exists. And what we have is that we can now find out what the parameters actually are. So at P0, we have that S0 is simply S of x0, y0. And we know that T, that we're relying on the Cauchy curve, so T is equals to 0. Okay. And this implicit function theorem is basically this condition. This solution exists provided the Jacobian, and the Jacobian is the derivative of the x with respect to s, the derivative of y with respect to s, evaluated at the point P0, the derivative of x with respect to t, the derivative of y with respect to t, also evaluated at the point of 0. You form a matrix that way, and you take the determinant. So the reason this thing works is we're basically linearizing the problem about P0, and we are writing down the condition that the linear transformation is invertible. Okay, and that is sufficient to actually show that the implicit function theorem actually guarantees a solution. So it's basically, you only care about the little point around P0, and that's why this is analysis I said was local. You linearize about that point, and you show that that thing can be inverted, and that's enough to guarantee that that solution exists. So here we have it. So what we now want to do is we have this Jacobian, which is formally expressed this way. In fact, the Jacobian of any transformation that has this type of form, you can always write in terms of the derivatives, and what you're doing is basically taking a Taylor expansion about a specific point. But what we now want to do is we don't a priori know what the surface is, and we don't know what the solution is, but we do know a tremendous amount about the way we've actually structured the argument. So what we're now going to do is we're going to write down this abstract Jacobian that we get from the implicit function theorem in terms of quantities we actually know, and quantities we know at point P0. Okay, so you can see this is what we're doing over here. So the first thing we know is we actually know the values of the functions x on the Cauchy curve, so that's just fs. We also know what the derivative is if we take the derivative along the curve. So remember, S parameterizes this curve. So as long as our derivative of x is along the curve, we actually know what it is. So we have that x of s0, 0 is simply the derivative of the functions we specified from the Cauchy data at S0. Okay, it would have been different, and you'll see this coming now, when we actually work out x of t. We have to use a different technique because then we're moving off of the curve, but we actually can. So that's the nice thing. So what follows these next steps is simply very carefully replacing this abstract Jacobian with things we actually know. You can do the same thing for y of s, actually, because you know it on the curve. But before I do that, we actually know what x of t is as you move off of that point, because x of t is basically swept out along this characteristic curve, and x of t is therefore just defined as the tangent to the characteristic curve that moves off, that we know to be a by construction. Okay. And so in a similar way, we can go along and say y of s is just the derivative of g along s. So we're looking at deviations along the Cauchy curve. So the derivative of y with respect to s is just g prime. And we also know that the derivative of y with respect to t is just b. Okay, so what we've done here is we've written our abstract Jacobian in terms of functions we actually know that have been specified in the problem. And so the condition that the Cauchy problem can be solved is just basically saying that that Jacobian, which we can now calculate, doesn't vanish. Okay. So it's kind of nice. You've reduced this very abstract idea of finding solutions that specify data to basically an algebraic condition of functions you know. And so you basically have this condition that this thing must be non-equals to 0 at every single point, P0, on the Cauchy curve, and then you can find your solution. If that happens to be the case for just some of the points, okay, and this is where it actually goes beyond the scope that I'm really going to focus on here, then you can still find a solution close to those points in which it is valid. But you have to treat the points at which it's no longer valid very, very carefully. And typically shocks start there. And I'm going to explore a little bit of what happens when that thing fails, as well as what you can say about it then. Okay. So, yeah. So anyway, so this is the important condition that guarantees the existence of the parametric surface. And so the very first thing when you're given Cauchy data, or for example, when you're given a differential equation and you're given the Cauchy curve and the initial condition, I always go and work out this combination, and I find all points at which it vanishes, because then I must be careful. I know I'm guaranteed a solution at all points at which it doesn't, but I pick out specifically those points at which it vanishes. So that's the first check that I do. Okay, because there in that region I have a local representation of my surface. So now we're going to look a little bit at what happens when it fails, or what in fact it means when it fails. And that's kind of cute too. Let's go on. Okay. So we now have our surface that's parametric constructed out of the union of characteristic curves. And if the local representation is guaranteed by this condition over here, then by the theorem of lecture 2, we basically have that the surface is unique. So all we had to do, because we have theorem 2 in the background, or theorem of lecture 2, that basically identifies the union of characteristic curves uniquely with the integral surface, and vice versa. The integral surface can always be described by the union of characteristic curves. We immediately have, once we've proven existence, uniqueness follows, which is nice. And we now have that any integral surface through gamma has to contain the characteristic curves through the points of gamma. Okay, so it's provided a very, very nice geometric picture of what solutions to first order curves look like. And it's a geometric picture that people have tried to generalize that didn't fully manage. Well, you can't to higher orders, but you can generalize some of it. And a lot of the ideas, like the importance of the characteristic curves, that was generalized, because you can find characteristic curves for higher order solutions, because you simply integrate these functions that have entered into the differential equation. So there's a mechanical way. So that was taken and run with, but you cannot do it in full generality like this in higher dimensions. Okay. Okay, so now let's just look at some of the implications of the fact that the Jacobian must not vanish. Okay, it's an essential condition to prove existence, and what I'm going to do is illustrate what happens if it fails. Okay, so let's assume it's 0, right? The Jacobian is vanished, so our condition for the solution existence from the implicit function theorem is no longer there. So we're basically going to assume this guy. And then we're going to look at the implications, okay? We know, in addition to that, that this expression is always true, okay? Why is it true? Okay, look carefully. It's not obvious, but it's always true. H's derivative is basically the derivative of z, which is basically the derivative of u along S. Okay, so it is always true that du ds, we're first going to do it generally and then evaluate it on the characteristic curve. Du ds is equals to du dx times dx ds. Okay, and on the characteristic curve, you here have the u of x, and then dx ds, we worked out in the previous slide, is just f prime. Okay, plus du dy times dy ds, which is just g prime. Okay, so this condition here simply follows from taking the derivative of u in the direction of this characteristic curve. Okay, so that thing is always true, and this condition is actually useful because we're going to use it in the subsequent lectures as well. So just know where it comes from. The second thing we have is just our ordinary quasi-linear equation up here. So let's just write it down there again. Okay, so that's just this thing up top here written out, and you can see that it has sort of the same structure. You have that the function c is equals to ax AUX plus BUY. Okay, so that holds. And so if you have this condition, that condition, and in addition, you have this thing to be true, you can work out a couple of consequences simply by eliminating the thing you don't know, which is UY and UX from these equations. And the way I would do it is simply I would divide this equation through by G prime and that equation through by B and subtract them. Okay, and so if I have that, when I subtract them, I basically have that uy vanishes. Okay, you have a over b is equals to f prime over g prime, which you have up top here, so that also vanishes, and you're left with h prime over g prime is equals to c over b. Okay, so that is one of the consequences. The second one is that you do the same thing and you try and basically get rid of ux over here. So you divide by f prime. So you have h prime over f prime plus g prime over f prime times uy. And here you're dividing by a. So you have c over a ux plus b over a. And if you invert this thing, you once again that this right-hand side exactly cancels that one, and you're also left with that condition. Okay, and if you look at this very, very carefully, this is basically the same condition as saying that your Cauchy curve is characteristic. Okay. So the fact that your Jacobian is failing, okay, in other words, the thing that ensures a well-defined solution is exactly equivalent to saying that at least at this point, your characteristic curve that you chose lies parallel to the characteristic lines. And that kind of makes sense. So that's the only case in which your solution fails. Okay. And even if it fails, you can still do stuff. Right, so you have no solution unless gamma is a characteristic curve, right? Because if gamma is not a characteristic curve, you can have an inconsistency. Okay, but if it is a characteristic curve, then you have a problem in that it actually gives you only the information about the characteristic curve itself. It tells you nothing about the solution of the characteristic curve. Okay, and then to get a well-defined problem, you actually have to take a different curve that goes through that specific point, and then you have to specify the data there. Otherwise, otherwise all you get is one curve, and you've said nothing more about the other curves, about the rest of the data. Okay, so no solution unless gamma is a characteristic curve, and therefore there are infinite many solutions, because you can imagine that if you've specified this curve in your data, the only condition that the rest of the surface has is that they actually have to be characteristic to the tangent vector up there, and that you can like switch everything. So you sort of have the idea, you've specified a line, and you can get any surface that goes through that line to do it. So you have a lot of freedom if you've not met this condition. Okay. So in order to restrict those infinitely many solutions, what people typically do is you take a different curve, say gamma prime, okay, and then you play the same game, and you just ensure that gamma prime is not characteristic, and then it passes through one point in gamma. So the main takeaway here is basically the condition that you can't find a well-defined solution fails only if your characteristic curve that you specified is actually, your Cauchy curve that you've specified is actually characteristic. And if you have that, you simply haven't restricted the solution, and you must do more work. Okay? If the solution is characteristic only at one point and then moves off being a characteristic, then you have a problem. Okay, then you have an inconsistency and you can't find a solution. Okay, so that basically is the geometry and the Cauchy problem. And as you can see, this Cauchy problem is pretty general, and what we're going to do in the remainder part of the lecture is actually look at specific examples. Okay, so the first, and this is kind of the problems you'll get, is typically problems of this kind, where you actually apply the theory that we systematically worked out in the past to actually get your surfaces out. And it's kind of cool problems, because you see what surfaces are possible from differential equations. So the first one is a linear partial differential equation. So this theory we've developed so far, and that we'll generalize in the next lecture, has been for quasi-linear equations. So the difference between a quasi-linear equation and a linear equation is simply the way the functions are chosen. So here we still have it linear in the highest derivative, so you have the ux and the uy, but the difference between linear and quasi-linear is that the independent variable can no longer appear in the coefficients. So it's actually a simpler case than what we've been looking on for what we derived the theorem. So you basically have a of x and y, ux, b of x and y, uy, and then that generalized function that we had previously, where we actually had, c of x, y, and u, we've now split. We've made it linear, so we actually have c, which is just a function of independent variables multiplied by u with another arbitrary function over here. And this thing is actually simpler than the full quasi-linear equation, because you can decouple the components. And the way you decouple it is simply you write out your characteristic equations. This is true for any equation. It's basically you write out your characteristic equations, and when you do that, you see that the equations that determine your characteristic functions is basically the x dt equals to a of x and y, and dy dt is equals to b of x and y. And so if you remember the characteristic equation from the previous slide, you actually had the third one. If it was not a linear system, you would have z entering here, and you'd have a third equation. So you've actually, in the linear case, you simplify the problem to having two equations that determine the characteristics for x and y explicitly in terms of functions. And whenever you have equations like this, that especially that don't have t inside here, they're autonomous, there's a trick that you can do, or rather a technique that you should have studied in the second year. But what you basically do is you can either try and solve them like this in some cases, but what you can also do is notice that this is entirely equivalent to this expression. Okay. And this thing basically is an ordinary differential equation, say in x. Okay. Which you've had a number of techniques to be able to solve, and typically the problems we have in PDEs actually chooses very simple functions here so that you can solve them. So the focus of this course is not the ordinary differential equations and all the techniques, but rather the partial differential equations. But basically what I'm saying is equations of this form you did in the second year, and if you have any doubts, and they're like 5 different techniques to solve them, they've been totally classified. There's some equations that you can actually, it was proven, the Paine-Levé equations was proven that you can never solve them, but they have been classified, so you can always reduce it to those equations. So it's a very, very well-studied field, and in the case of a linear PDE, you can reduce your partial differential equations just to one PDE. Okay, so this thing then describes, you can solve it hopefully using the techniques in the second year, to a function of y, or in terms of x, okay, or an implicit function of the two. And what this does, it simply determines curves in your xy plane. Okay, so instead of looking at this this surface in 3 dimensions, we now are looking at what the projection of that surface, the characteristics on that surface will look like in the xy plane. Okay, and those things we call characteristic projections, and the full curve is then computed by taking this thing and then putting it back. Once you know the actual solution x of t and y of t, and putting it back into the linear equation. Okay, in the following way. Okay, so the technique, if you have a linear PDE, write down your characteristic equations, they decouple. You can either solve it directly from there, or you can equivalently write this thing down, try and solve it. It gives you lines in your xy plane. Get those lines, parameterize them, and then put them back into this, the characteristic equation for z, just using c of x and t, which comes from that equation, times z plus d of x and t. Solve it, and you've solved your problem. Okay. And so let's take it even one step simpler. So this is true for all linear PDEs. The simplest linear PDE that we had was that advection equation that I actually solved very quickly, or sort of gave you an intuitive feel at the beginning. And I just want to apply what we've done, like the formal theory, because the nice thing about linear ODEs is there's a recipe that you can step through. So let's just step through this recipe for the advection equation. And so there we have the advection equation. All of these fancy functions have collapsed into one constant. And we're going to solve the advection equation with a specific initial condition. Okay. So the first thing we do here is, from our initial condition over here, we specify the Cauchy curve. Okay. The Cauchy curve is basically you're moving in x while you are keeping y constant to 0. So your x is simply your parameter s. It indicates where along your line, your Cauchy curve you are. And then you have that u, which is basically the height above the xy plane, which we've denoted z, is just defined by h of s. Okay, so this step takes a bit of practice, but it's important and it's really straightforward. So you simply write down, if it's an initial condition, you write down your curve in the xy plane and you put z equals to h of s. Okay, so that's the initial conditions. The next step is you write down your characteristic differential equations, and that's basically saying x dot is equals to the coefficient of ux, y dot is equals to the coefficient of uy, and z dot is equals to the function on the minus the function on the right hand side. So there we have it. X dot is equals to c, y dot is equals to 1, and z dot is equals to 0. Okay, so that's our differential equations. And so to find the surface, we actually have to solve this differential equation with that initial condition. And this differential equation with that initial condition, and this differential equation with that initial condition. So if you look at this thing, you can immediately see that solving this guy, we have the x to t is equals to some constant. Okay, so we have that the solution is just ct integrated with respect to t plus an arbitrary constant, but that arbitrary constant is such that x at t equals to 0 is s. Okay, so we put the s in there. So we have the full parametric representation of x. The next step is to do the same thing for y. We have that dy dt is equals to 1. Integrating that once, we have that it's equals to t plus some arbitrary constant, but that arbitrary constant is 0 because we know when t is equals to 0, y is equals to 0. So we have that solution. And then the final one is simply that dz dt is equals to 0. And we know, so z is constant, and we know that that constant is h of s. Okay. So that is our full parametric representation. And it's important to be able to do these steps. Okay, this is the easiest example. In the general cases, you're actually going to have functions of x and t entering in here, and possibly z if it's not linear. Okay, so if it is linear, then you do this trick and you try and solve it. If it's non-linear, you try and see if there's a interesting way in which you can try and order the way you solve it, because often you're going to have that you can solve the function, say, for z or for y explicitly, and then you can, in terms of time, and then you can plug it back in and then get the other solutions. Okay, so there we have a parametric representation for the integral surface. Now we basically need to go through the steps that we did to actually work out the conditions for its existence. And it just illustrates it. We want to eliminate s and t. So here it's easy to eliminate t. T is just equals to y. So we put that into that expression. And then you get s is simply equals to x minus cy. Okay. So that comes from the second equation. S is equals to x minus cy. So we actually have the complete inverted version of what our parameters are now in terms of the coordinates. And the moment you do that, you can actually use that to put it back into z, and you have that the solution is z is equals to some function h of x minus cy. So you can actually see now rigorously step for step how our method of proof for the solution actually gives a method of proof for the existence of the solution actually gives a method of proof for finding explicit solutions in almost all the cases that we've looked at. Okay. In fact, the only thing that stops you from finding the solution is if you're not practiced at solving these differential equations. But in practice, they can all be solved, or at least reduced to simpler functions. Right, so this is the simplest example. This then is in some sense, our characteristic variable, the thing along which the function remains constant. Now let's step it up a little bit and look at an equation like that. Okay, so this is Burgers' equation. It is a non-linear equation because there you have actually the dependent variable multiplying the front of x. It's a very interesting equation, and we're going to solve it where we've actually specified, rather than the general Cauchy problem, the initial value problem. So this equation was studied by Henry Bateman, which is a very interesting character. Actually, he's got this legendary reputation at Caltech where I was. He was amazing. He would, just for hobbies, collect integrals of difficult functions. In fact, after he died, he would and he wouldn't even publish them, which was a great annoyance to some of his colleagues. He would simply work it out, see what it is, and then file it in his desk drawer. And so after he died, a group of graduate students that actually knew him well went into his desk drawer, scrabbled out all the random pieces of paper, and basically looked for all the integrals that were not published. And they spent about more than 2 years doing it, and the result was, I think, 2 or 3 books just of integrals, and they called it the Bateman Manuscript Project. And we actually learned a tremendous amount. So integrals that previously couldn't be solved, he just stashed in his desk somewhere. And so those 2 books, if you're ever looking for integrals that you don't know how to solve, like that arise from partial differential equations, because what he did, he would try and solve various problems, and then those dy dx would arise, and then it would be a matter of pride, I guess, for him to just be able to solve that. And he collected them. And so the Bateman Manuscript Project was there. In fact, I've got the 2 books of integrals that he has, because when you go and do research, you eventually start looking for integrals that you can solve analytically. If you're me, rather than doing it numerically immediately, because there's a lot of power in that, because you actually have the parameters that you can then see that goes into the model that allows you to see how the thing actually changes. So they did that, and so most of his life's work is now in those books, but they've also been incorporated in, there's another place for looking for integrals that I'll actually give you the link later on, is the Los Alamos they have like a book that's now online. That's actually free. That's very, very useful for going and looking up solutions. So if ever you get a partial differential equation or any differential equation, you get stuck, go and see if somebody else hasn't worked out the integrals, and most probably the answer is yes. And there's a very high probability that the dude who did it first was actually Bateman, okay, if it's non-trivial. The second guy that studied it again, more with a specific Bateman, I guess it was just an exercise, it was a mathematical game for him, he's a mathematician. This guy studied it more in terms of physical application, and did a lot of the properties and looked at it more. Okay, and this thing appears many places because it's some sense a simplest non-linear equation. It appears in fluid mechanics in waves. It appears in acoustics. It appears in gas dynamics, traffic flow. And the reason it appears, it's the simplest equation that causes shocks. Okay. And a lot of these, if you want to have a physical thing, intuition for what the U is, it's often the velocity field. So it's the velocity at which particles, say, in the fluid are moving. Okay. It has a number of properties. It demonstrates conservation. It has conservation equations, which we'll look at a little bit later. It can develop shocks, and it has another way to be expressed. Okay, and this is actually the conservation form that you can actually use to derive certain theorems from. So this conservation form, just to see how you get from here back to the original equation, simply this is u squared, the derivative. So if you take the derivative, you have ux. Okay, but it's actually useful to know it can be written that way. Okay, so what I'm going to do now is I'm going to use our same techniques and write down the parametric solution to this equation. And it's basically to illustrate how powerful the method we've just explored is. So firstly, you're specifying an initial condition, which is the velocity distribution on gamma. And gamma, we're going to say, is the curve that's parameterized by x. It's an initial value problem, so y is equals to 0, where y here basically plays the role of time. And then we specify the initial profile. So it's almost exactly the same as that advection equation we solved previously. The only difference comes in with the characteristic differential equations. Okay. Once again, we just have dx dt is equals to a, okay, which is basically u, but we're working on the characteristic surface, so we consider u to be z. Okay. So here we have something that's not linear because we have z. And implicitly, when z appears on the side, I always, just to stop making mistakes, put in that it's a function of t. Okay, it's not known, it's an unknown function. So this is definitely not the equation you're going to go about solving first. The other equation is dy dt is equals to 1. Okay, so dy dt, you have the case, is equals to b is equals to 1. And this is the equation you solve first because you can. Okay. And then dz dt is equals to 1, which you can also solve because you can. Okay, so you go about, once again, solving this, and the solution method is exactly the same as what we did for the advection equation. dz dt is equals to 0, so z is a constant in time, and that constant is equals to h of s. Dy dt is equals to 1, so integrating you have that t occurs there plus a constant, which is 0, and once you have that, you can work out the parametric solution. Okay. And the parametric solution is x equals to s plus zt. Okay. This thing you can only write down since you know that z is constant. Okay. If z was not constant in time, this would not be true. Okay, so rather follow what I've said. Systematically solve these two first. You know z is a constant, and therefore you can integrate this last equation. Okay, and you also know that when t is equals to 0, x is equals to s. Okay, so that's a parametric solution. y is equals to t and z is equals to h of s. So actually the way I've done it here is, well, it's the right solution, but the order I've presented it in is actually deceptive. I would always work out y equals to t and z equals to h of s first before I try and solve this thing. Okay, so the next step is to eliminate s and t according to exactly the way that we proved the existence. And the way you eliminate s and t is you immediately have that t is equals to y. Okay. And you can use this function next. Okay, so t is equals to y. Z is a function of h of s. Okay, so here I'm replacing z with u on a parametric surface, and then I'm saying s is equals to x minus ut. So this is an implicit equation. I haven't solved the equation explicitly because I still have u appearing in there. Okay, and this is what makes the burgers. This is a very good way of exploring the solution, and it was only accessible because we know the theory of solving the partial differential equations. And it also gives a lot of insight, but it is not an explicit solution. Okay, so here u is still implicitly of a function of x and y, and what we're going to basically do now is look at what this solution behaves like for a specific h. Okay, so h is given, and then from h you know that the equation obeys this implicit solution, and now let's look at some of the properties. So the first thing we're going to do is work out the characteristic projection. So remember when we were doing the linear equations, the characteristic projection was easy. It followed straight from the actual coefficients in front of your partial differential equation. Here, you actually have to work out the characteristic projection using these equations, where z is now changes for every single problem. Okay. Okay, and that characteristic projection basically is this thing. X is equals to s plus h of s times y. Okay, where I've taken it from this equation. So z is now h of s. S is there. Y is just your t variable. Okay, so here is because it's a nonlinear problem, or a quasi-linear problem. Here we actually have that the initial condition determines what the characteristics look like. And it's a very good illustration because in almost any problem that's not linear, this is the case. Okay. And what you can say is, one, this is the characteristic projection onto the xy plane, but you can also say along the specific line, this u equals to h of s is constant. Okay, so in the case of the advection equation, we had that the wave just continues to travel and remain constant along straight lines. We still have that u remains constant along the characteristics, but we have that the characteristics are dependent on the actual initial function. And so what happens is something as follows. So let's take the same initial condition as what I had for the advection equation. So we just begin with a hump function. Then what we do is we work out the characteristic lines projected into the xy plane. So we basically are going to work out for each s, x is equals to s plus h y of s. So what that is a whole bunch of lines that look like this. So look, when y is equals to 0, we're basically on this axis over here. Okay, so then s is just the x value. Okay, so it's uniformly distributed. Then you have the slope, so you can invert this thing and say y is basically equals to x over h of s minus s over h of s. Okay, so you basically have the slope that then changes. The larger h of s is in this bump over here, the inverse 1 over h of s becomes sort of pushes the lines to be skewed that way. So you can actually now see that the characteristics are very closely related to the initial condition, or basically influenced by the initial condition. And it is along these lines that the function surface actually remains constant. So you have the strange situation where two of these characteristic lines can actually intersect. Okay, so for example, you were to take two lines, say this one over here and that one over here, so that's S1 and that's S2, they go along, or maybe that's a poor result. Let's take just beyond 0. Okay, let's take that to be S1 and S2. These two go along until they eventually intersect over there. And then you have a problem, and it also illustrates the second way in which existence breaks down. So we showed, when we did the Cauchy proof, I said it was local, right? It was around a specific point. The only thing that we guaranteed with the Cauchy problem is that a local solution exists, and we didn't say how far around that point. And this year you can start seeing what limits how far is when the actual characteristic curve starts colliding. Okay, and we can work out what this intersection point is simply by putting various values of s into this characteristic projection equation, and we have something like that. So any two lines that starts with s greater than 0 actually intersect at this point. Okay, so the smallest value for which this occurs is basically what limits when the solution is still single valued. Okay, and then you can further go on and say if H, which is our initial condition over here, has compact support, and that basically means that it is non-zero only in a small region and it goes to 0 at infinity as well as its derivative, then you can guarantee that at some point you actually, these characteristics collide and it goes singular. And they collide whenever the h derivative is less than 0. In other words, what basically happens is over here, the derivative is negative, and you have that the one line tips over more than the one below, and therefore they're guaranteed to collide. Okay, and the physical interpretation that Berger's actually brought to the table was basically the higher velocity points collide with the lower velocity points in front. And this method in which it happens is known as a shock. It was the typical example of shock waves, and if you actually do the full 3D solution, you have something like this. So this is our characteristic projection in the xy plane. So you can imagine I shift this thing and I put it underneath, okay? And what happens is along a specific characteristic, we proved in the previous slide that the height of the surface remains constant. Okay, so this is kind of the surface you have. You can see that here is our initial hump function, and then these characteristic lines, the value remains constant along there, but the ones over here tend to run more quickly. So you can actually see with a high velocity, it tends to catch the ones that have low velocity in front of it. And you can actually compute what happens is that when these high velocity points actually collide with the ones in front of it, this line here goes vertical, and that's when the shock occurs. Okay, and that also occurs at the same point at which the two characteristic lines intersect, and you can actually compute what that is. And the way you compute what it is for this particular example is you simply work out the point at u of which u of x goes to infinity, and the way you work that out is you simply say u of x is equals to h prime with respect to x over 1 plus h prime of s over y. Okay, so that is what u of x is, and you can see that this dude becomes infinite when this thing goes to 0, and it gives you that y is then equals to minus 1 over h derivative of s. And you can also see that occurs in this condition where we simply worked out the condition for the intersection points. If you simply take S1 approaches S2 and you use your definition of a derivative, then you have exactly the same thing over here. Okay, the smallest value y star, in other words, this point where the lines first collide, is simply occurs when S equals to S0 and H prime is at a minimum. Okay, so to get the lowest point at which this thing starts colliding, you can simply evaluate the point of your initial condition where H prime is where its derivative is a minimum, and that is something you call a gradient catastrophe. Okay, and this behavior is ubiquitous in any nonlinear partial differential equation. Okay, shocks is not a surprise, it always happens. It causes a lot of problems for people that try and numerically integrate it, but it's always there, and there are actually techniques for coping with it, and a lot of those techniques were first developed in partial differential equation theory before they then became numerical in the last 50 or 60 years. The last thing I want to do is just give you an indication. So all I've done is here plotted the initial condition, plotted it at a later time, and plotted it at a much later time. And here you can see, because this thing, the top thing, the speed actually moves faster, the wave tends to eventually break over, and after it becomes vertical, you no longer have a single valued solution, and that's why they call it a gradient catastrophe. Strictly speaking, even though you can write the surface out, there's no strict solution. You can still find one numerically, and in practice, nature always finds one. For example, when the wave breaks over, you still have this funny surface that goes forward, and you can work approximations out for that, but you no longer see one. So your mathematical requirement is you're differentiable once, and that the solution is single valued, that's failed, but you can still do a lot with solving the problems, and people do that. And in fact, I'll actually give an example of how you cope with that in the next lecture. So just at this point, it's not easy to see in this thing, but if you actually were to draw a vertical line, you would see that you have 3 points going through that solution. And they basically call that the shock front, and then you cope with it in various ways I'll look at the next time. And then this is just what I've said, or summarizing what I've said. It's typical for nonlinear PDEs, and there are ways of coping with it, and they typically call these ways of dealing with the shocks weak solutions. But they're not in the class that we've rigorously solved or proved that the Cauchy theorem is well defined and the solution exists. Okay. And I think that's all. Yeah, that's all for me for today. Thank you very much. Any questions?
No, I'm fine, thanks.
You're fine. Okay, good. Yeah, so next time I'll start giving an example of the weak solution, and then I'll also start putting up the problem set that you have some time to play with it yourself. There was a lot of content here. It's very nice stuff, but you only make it your own if you actually go through an example. The nice thing, however, is that it's algorithmic. If you follow the steps that I did in the examples, almost every single time, well, every time if you can integrate the equations, you are getting an answer. And all the examples you'll get, you'll be able to integrate the equations. So don't stop until you actually have an answer. And the last thing I must say is partial differential equations are nice because they're easy to check. Once you have an answer, write down the answer, differentiate it, and make sure that your initial equation is satisfied. That's a necessary check, and you can catch a lot of mistakes that way. So it's sort of a self-verifying approach. Anyway, so thank you.